Hello, this is Mrs. Evans and welcome to your Module 2 crash course video, the short version. This video should help you review quickly for a Module 2 DBA or a Module 2 exam. You're also welcome to jump back anytime during the segment to use this as a refresher on the Module 2 material. As a reminder, you worked through 7 different lessons in Module 2. You can pause the video at this point to take a detailed look at all of the skills that you are expected to understand for Module 2. We're going to visit each of the lessons and do a brief review of the content. Let's start with 2.01, where we learned about rational exponents. Rational exponents are very useful when it comes to helping us work with both exponents and radicals. In this diagram below, you can see that the conversion between a radical expression and the rational exponent form is we take the exponent and put it in the numerator of the rational expression. We take the index or the type of root and put it in the denominator of the rational exponent. This symbol right here is what we call the radicand. Whenever it has something other than a blank symbol, we'll call it by the number in front. So for example, this first term is not a square root, this is the cube root of positive 2. Let's say we want to change this cube root to positive 2 into rational exponent form. We see the index is 3, but we don't see an exponent. So one good option is to rewrite this with an exponent of 1. And what that tells us is our base is 2, and we're going to rewrite that with the index in the denominator and the exponent in the numerator. So the cube root of 2 is equal to 2 to the 1/3 power. We can go backwards from rational exponent form by simply replacing the 1 for the exponent inside the radical and the 6 as the index. Whenever we have 1 for an exponent, we do not have to keep that exponent. So I'm actually going to rewrite this as just the 6th root of 2. We know the exponent is 1, but we don't need to write it. This next example shows both a variable and a coefficient inside parentheses. What that means is this entire term, 10n, belongs underneath the radical. And it's a good practice to keep it in parentheses so that we know it's not just the variable that receives the exponent, it's the variable and the coefficient. So we're going to put our base in parentheses, put our radical symbol. The 2 is going to go out front, and the 3 goes inside as the exponent. Now we could leave off this 2 and just keep this as the square root of 10n cubed. Finally, we'll transform an expression that can also be simplified. So we have negative 125 to the 1/3 power. Well, if we put our negative 125 underneath our radical, the 1 goes here and the 3 goes here. Technically, this is asking you for the cube root of negative 125, or basically what raised to the 3rd power gives you negative 125. Well, we know it has to be a negative because in order to raise something to a power and get a negative, raise something to an odd power and get a negative, we need a negative number as our base, an odd number of negatives. If you think back to the perfect cubes list that's in Module 2, you'll know that 5 cubed is 125, so negative 5 cubed is negative 125. So this is an example of an expression that can simply be evaluated further. Let's apply some of this to the properties of rational exponents that you learned in lesson 2.02. The first property is what we call the product property, and it says that when we take the product of two powers, we add the exponents, assuming that the bases are the same. Now right here, we have 2 radical expressions. So before we can actually apply this property, we need to do a little bit of rewriting. So the first thing I'm going to do is to take each of these expressions and write them as a rational exponent. The cube root is equal to the 1/3 power. So I'm going to rewrite this as 16 to the 1/3 power times 4 to the 1/3 power. Now we have another issue in that we don't have the same base. So if we get creative, we know that 16 is 4 squared. And we still don't quite have the same base because 4 squared is not equal to 4. However, we could multiply these two exponents, kind of jumping down to this power, and say we have 4 to the 2/3, because 2/3 times 1/3 is 2/3, times 4 to the 1/3. If we add the exponents, we get 4 to the 3/3, which is just 1. So the final answer to our expression is 1. Our next property is the quotient property, which says if we divide two powers with the same base, we're going to do the opposite of multiplication, and we are going to subtract. So when we multiply powers, we add. When we divide powers, we subtract. Again, we don't have the same base quite yet, so let's do a little bit of rewriting. First things first, let's get this into exponent form so we can apply the exponent rules. So we're going to rewrite the cube root of 9 as 9 to the 1/3. And the fifth root of 27 is 27 to the 1/5. Now we're going to rewrite both terms inside with a base of 3. 9 comes from 3 squared, and 27 comes from 3 cubed. Now we can multiply the exponents so that we have 3 to the 2/3 divided by 3 to the 3/5. And then what we're going to do is we're going to subtract the exponents. I'm going to do that down here at the bottom. So we're going to have 2/3 minus 3/5. Common denominator is 15. So 3 times 5, 2 times 5. And then 5 times 3, 3 times 3. So we have 10 15ths minus 9 15ths, which is 1/15. So we're going to get 3 to the 1/15 power. Seems kind of weird, but we're just applying those properties of exponents by having the same base first. And this also requires us to use multiple properties at one time. Now, obviously, this third example here, we've kind of covered this already, but I wanted you to see it one more time. We have y to the 4th raised to the 1/6 power. So when we raise a power to a power, as you already know, we have y to the 4/6. 4 over 1 times 1 over 6 is 4/6. The important part of this example is that sometimes when you multiply exponents, you won't always get a simplified exponent, and that is what we want, y to the 2/3. Or, if you remember correctly, to convert this to radical form, we would have the cube root of y squared. The format of your answer will depend on what the question is asking for. Finally, you learn how to manage negative exponents. And whenever we have a negative exponent, we simply move the expression that has the exponent across the fraction bar, or we think of it as the reciprocal. We don't take the reciprocal of the entire expression, we just move the piece that has the negative exponent. So we're going to flip this, and we're going to get 1 over 27 to the positive 2/3 power. But we can simplify this, because we can write this as 1 over the cube root of 27. And then you may not realize it, but you have the option of where you put the exponent. You can put the exponent inside, but man, 27 squared seems like a large number. I do know there is a cube root of 27, so if I find that cube root first and then square it, my math will be a little easier. So the cube root of 27 is 3, and 3 squared is 9. Moving forward in Module 3, you then learned how to solve radical equations. There are 4 basic steps to solve any radical equation. The first step and most important step is to isolate the radical. This makes our math much easier throughout the process. The second step is to square both sides if it is a square root. If it is a cube root, for example, then we would raise both sides to the 3rd power. So the type of root determines what power you raise both sides to. Once you do that, your variables should be able to be isolated, and then finally, when you solve your equation, you'll check to see if the answer is extraneous. So let's practice this with this one. We're going to isolate the radical by subtracting 10 from both sides. So we get the square root of 10m minus 1 is equal to 3. Now we are going to square both sides, since this is a square root. These are inverse operations, so raising both sides to the 2nd power cancels the square root on the left side. We're going to add 1 to both sides to isolate the variable. And we get a nice, easy number as our answer, m is equal to 1. You should always check your answer when you are solving radical equations because you can come across what we call extraneous solutions. Extraneous solutions are answers that you get that don't work in the original equation. They are introduced in the point where you are squaring both sides. And sometimes they are not introduced, sometimes they are, depends on the equation. For this equation, I don't expect an extraneous solution because when we squared both sides, we were squaring a positive, not a negative, and we are not squaring a variable. Usually a negative or a variable being squared is what introduces the extraneous solution in the square root equation. So we're substituting our answer in place of x, or m, and we are going to simplify to see if it makes the statement true. So 10 times 1 is 10. 10 minus 1 is 9. Square root of 9 is 3, positive 3, not negative 3. And 10 plus 3 is 13. Since both sides work, we call this a non-extraneous solution. Think of it as non-extra, whereas an extraneous solution is extra. It doesn't belong. Halfway through the module, you switched gears and you started working on complex numbers. Complex numbers are all based on the premise that I, the imaginary unit, is equal to the square root of negative 1. So the first thing you learned was the cycle or powers of I, and I cycles through 4 different values. If I is equal to the square root of negative 1, then I squared is actually equal to a real number. If we take both sides and we square it, the radical cancels here, and we are left with I squared is equal to negative 1. Then we have I cubed. I cubed can be rewritten as I squared times I to the first. I squared is equal to negative 1, so really we're saying we have negative 1 times I, which is negative I. I to the fourth can be creatively rewritten as I squared times I squared. And if we substitute negative 1 in place of each I squared, we get negative 1 times negative 1 is positive 1. And then if we were to continue this pattern, say I to the fifth, we could rewrite that as I to the fourth times I, and we know I to the fourth is 1, so I to the fifth is going to be equal to I. And if we keep going, we're going to continue to see this pattern. So what we do is we look for any power of I where I to the fourth can be removed. If I to the fourth is positive 1, every time we remove an I to the fourth, we're lowering the exponent to something that's more familiar. Our goal is to get to I squared, or I cubed, because we can rewrite those as values. So let's say we have I to the seventh. I to the seventh can be rewritten as I cubed times I to the fourth. I to the fourth is equal to 1, and anything times 1 is itself. So really, I to the seventh is equal to I cubed, but we know I cubed is equal to negative I. Let's look at I to the 22nd. I to the 22nd is a little bit more challenging because it's a larger exponent. Let's say we took 22 and we divided it by 4. 4 goes into 22 5 times with a remainder of 2. We know that every time 4 goes in here, I to the fourth is going to be equal to 1. So what we're really looking at is the remainder after we take out as many I to the fourth pieces as we can. Well, we're going to take out I to the fourth here 5 times, and we're going to be left with I squared, or negative 1. I to the 30th, 30 divided by 4, let's see, 4 times 7 is 28. So again, we have a remainder of 2, and that means this one is also equal to I squared, or negative 1. Let's say we have I to the 17th. 17 divided by 4 is 4 with a remainder of 1, or I to the first, which is I. So you're basically taking your exponent and dividing by 4. The remainder is either going to be 1, 2, or 3, and then that lets you pick I, -1, or negative I. Now we use this later on in the module when we're working with complex number operations, but the power of the negative square root allows us to simplify negative radicals. Let's say we have the square root of -49. If you remember, there is a radical property that says that we can break a radicand into two separate expressions, two products, and we can square root these separately. So I can rewrite the square root of -49 as the square root of -1 times 49. I can square root each part separately. We know the square root of -1 is I. The square root of 49 is 7. So the square root is 7i. Likewise, it works on radicals that are not perfect squares. For example, the square root of -72 is going to be broken down to -1 times 72. And we know that the square root of -1 is going to be I, but 72 is not a perfect square. We can rewrite it as 36 times 2. So when we square root the I, the -1, we get I. When we square root 36, we get 6. But we're going to be left with this 2 under the radical because it cannot be square rooted. We can take a similar approach with the square root of -50. Square root of -1 times 50. I'm going to rewrite this as -1 times 25 times 2. So again, square root of 25 is 5. Square root of -1 is I. And we're left with a square root of 2. We always write imaginary numbers with the coefficient in front of I, and it's the term with I is called the imaginary term. And then we might have it where we have an addition or subtraction with a real number. So combined, these are called complex numbers. And sometimes it's necessary to have the conjugate of an imaginary number, which we'll use on the next page. If we take this plus and change it to a minus and bring down the two terms before and after, this is our conjugate. So anytime you're writing a conjugate, just change the sign between the real and imaginary part. Let's play with some operations on complex numbers. Let's say that we want to add 3 plus 2i with 4 minus 7i. When we add or subtract complex numbers, we simply treat them like polynomials, where we add the like terms. So we are going to add 3 plus 4, which is 7. We're going to add 2i and -7i, which is -5i, and that is our answer. You can put complex numbers in parentheses if you want. Let's say we wanted to subtract these same two complex numbers. You have two options. You can distribute the negative, or you can read the problem from left to right. I prefer to read the problem from left to right since it simply means less work. So the first thing we will do is 3 minus 4, which is -1. And then we will do 2i minus -7i. So 2i minus -7i. When we subtract a negative, we add the opposite. So 2i plus 7i is positive 9i. Let's say we want to multiply these two numbers, 3 plus 2i times 4 minus 7i. We apply the same property that we would with polynomials and we FOIL. So 3 times 4 is 12. 3 times -7i is -21i. 2i times 4 is 8i. And 2i times -7i is -14 from 2 times -7. I times I, or anything times itself, is squared. Combined like terms, we have 12 minus 21, -21 plus 8 is going to be -13. with I included. Now, when we bring down the negative 14i squared, we cannot leave I squared. If this was x squared, that would be okay. Since this is I squared, and we know from previous work that I squared is equal to negative 1, anytime we see an I squared, which is very frequently, we replace the I squared with negative 1. So when I bring down this negative 14, I'm going to change the I squared to negative 1. And what that really does is it changes the negative 14 to a positive 14. So some students automatically jump from negative 14i squared to positive 14 because we predict that change. 12 combined with 14 is 26, and then minus 13i, and there's our product. Our final operation is division, and my personal theory is that if you know how to divide complex numbers, then you automatically know how to multiply, subtract, and add. The one challenge with complex number division is that it does not feel like division until the very last step. And the reason why is when we divide two expressions with an addition or subtraction sign, we have to do a lot of extra work to make this something that can be divisible. Right now we cannot divide because the denominator is 4 minus 7i, and we have to get this down to a single real number that we can divide into both terms in the numerator. This is where your conjugate comes into play. When you divide two complex numbers, you multiply by the conjugate of the denominator. If you remember, the conjugate is the same complex number expression with the sign changed. So here we have 4 minus 7i, the conjugate is 4 plus 7i. Whenever we multiply one part of a fraction by a value, we have to multiply the other part. So we multiply the numerator and denominator by the same thing. This becomes one giant multiplication problem. Multiply in the numerator and the denominator. So in the numerator, 3 times 4 is 12. 3 times 7i is 21i. 2i times 4 is positive 8i. And 2i times 7i is 14i squared. I'm going to squeeze this in here. In the denominator, we're going to have these two expressions FOILed. 4 times 4 is 16. 4 times 7i is 28i. Negative 7i times positive 4 is negative 28i. And then 7i times negative 7i is negative 49i squared. So I'm going to bring this down a little bit, and we're going to combine like terms. In the numerator, we have 12 plus 21i plus 8i is 29i, and we have positive 14i squared. In the denominator, we have negative 28i and positive 28i, which cancel, and we're left with 16 minus 49i squared. Remember that I squared changes the sign of the term it's attached to. So I could cross out this I squared and make this negative 14, and I can cross out this I squared and make it positive 49. Then I combine like terms. In the numerator, I have 12 plus 14 is 26 plus 29i. And the denominator, 16 plus 49 is 65. At this point, I am allowed to divide if I want to. It is okay if I leave my answer this way, but technically, because I have a real number in the denominator, I should be separating each part. And this is why we call it division, because at the very end, we can write the numerator split into two fractions with a real number in the denominator. Let's round out this module with a brief review on polynomials. When we work with polynomials, it's very much like working with complex numbers, with the exception that we don't have to worry about powers of I. Let's review all of 2.07, where you learned about ascending order, classifying by term, and degree. And we're actually going to change this to descending, because when we write polynomials, we really want them to be in descending order. Ascending order means we go from smallest exponent to largest. Descending order means we start with the largest exponent and go to the smallest. So our first example is already in descending order. We're going to classify by terms, which means we're going to count the number of terms. Since we have two terms here, this is going to be a binomial. The degree of the polynomial is simply the highest exponent. Here, the highest exponent is 3, so this is third degree, or degree 3. Our next example is going to be a little more challenging because we have a mixture of variables. So right here it says we want to write this in descending order, and unless we're told which variable to use, we should assume that we'll go alphabetical. So we're going to write this in descending order by the variable x. And that means my first term is going to be the negative 6x cubed y squared because that has the largest value of x for the exponent. Now I'm going to pick the next highest x term, 12x squared y cubed. And then I'm going to keep going with the negative 2x and then finally the 3y. Because this has 1, 2, 3, 4 terms, this is a polynomial. And the degree is a little trickier because we have to look at the sum of the exponents on the leading term. On this first term, the sum of the exponents is 3 plus 2, so this is fifth degree. Our final example is pretty close to descending order. We're going to start with our term 5a cubed, but the last two terms need to be switched. So we're going to put minus a squared and then plus 2a. This has 3 terms, so it is a trinomial, and the highest exponent is 3, so it is third degree. We'll conclude our review of Module 2 with some polynomial operations, and this will feel very familiar because we've already reviewed complex number operations, which are very similar. So we're going to start with addition. When we add polynomials, we add the coefficients on the like terms. So 2x squared plus 3x squared is 5x squared. 3x plus negative 4x is negative 1x. And negative 7 plus negative 10 is negative 17. With subtraction, you can either subtract left to right or you can distribute the negative and then combine like terms. I like to just subtract left to right because it's less writing for me to do. 5x squared minus 2x squared is 3x squared. Negative 12x minus 3x is negative 15x. 1 minus negative 7 is 1 plus 7, or positive 8. When we multiply, we're going to multiply coefficients and add exponents. So multiplying two monomials, negative 2 times 5 is negative 10. X squared times x is x cubed. And y times y to the 7th is y to the 8th. Remember, any variable without an exponent has an exponent of 1. Our next example is more of a classic distributive property. We have 5x squared distributed through. So 5x squared minus 2x to the 4th. 5 times negative 2 is negative 10. X squared times x to the 4th is x to the 6th. 5x squared times 3y. 5 times 3 is 15. X squared times y is just x squared y. Nothing we can do about that term. It's just a mixture of variables. Then we have 5x squared times negative 6, which is negative 30x squared. Then we have the multiplication of two binomials, or a binomial and a trinomial, and so forth. So two binomials, we apply FOIL, first, outer, inner, last. So x times x is x squared. X times negative 3 is negative 3x. 2 times x is 2x. And 2 times negative 3 is negative 6. And then we combine those middle terms to get x squared minus x minus 6. Now, when you get into larger polynomial multiplication, sometimes it can be a bit tricky keeping track of everything. So you can use the distributive property twice. You can distribute the 2x through the trinomial and then the -3 and combine like terms. I like the option of making this a grid. So what I do is I take the binomial and I write it on one side, the side with the 2 rows, since there's 2 terms in a binomial. And I take the trinomial and split it on the other side over 3 columns, since there's 3 terms. And I just multiply this in a grid. It's the same as distributing the 2x through the trinomial. So 2x times 4x squared is 8x cubed. 2x times -5x is -10x. And 2x times 1 is 2x. Then we distribute the -3. -3 times 4x squared is -12x squared. -3 times -5x is positive 15x. And -3 times -1 is -3. So what we need to do is we need to combine like terms, and oftentimes you're going to find your like terms on the diagonals just because of the way the grid is set up. It's very easy to find them. So there's our like terms. As we combine them, we'll write the final answer below. So 8x cubed. -12x squared minus 10x squared is -22x squared. 15x and 2x is 17x, and then plus 3. Hopefully you found this a useful review for working on these skills in Module 2, which are rational exponents and radicals, solving radical equations, complex numbers, and polynomial operations. Remember, you can use this multiple times throughout the segment to review for a test, a DBA, or your final exam. I hope you enjoyed it. Have a great day.